Yamila is an assistant professor at the Leiden Observatory, and she's a researcher at SRON, which is the Dutch Space Research Institute. Previously, but also lately extraordinarily successful in gathering money from all over the globe, I should say. So it's a huge congratulations for winning the consolidation grant. So she just won an ESC consolidation grant, but she also got previously various Dutch funding, which is, when I remember correctly, not entirely easy, because the Dutch funding landscape is a bit obviously. So that's amazing. And then lately she also got the NASA Honor Award for early career contributions to the Juno Prime mission. So absolutely amazing. So I'm even more happy that you join us here today for your talk, for this colloquium talk. I think it should also be noted that Yamila did her undergraduate actually in La Plata National University in Buenos Aires. So you have had quite a travel around the world. So you're very experienced and living in different cultures and accommodating yourselves in there, and then even getting the funding from completely different funding agencies. So absolutely amazing. So maybe I leave it at this, and I leave you the stage for your talk with
Thank you. So, hello everyone. I hope you can hear me well. Great. Okay. Thank you so much for that nice introduction. So today I will be telling a little bit about what we do in my group. I'm in Leiden these days. I get something here, but it's okay. So let me start with that a little bit. So I put in the talk different topics, and it's mostly about giant exoplanets. But I will say a little bit about rocky exoplanets. I know here some people is interested in that. I know Helmut is here, so I will tell a little bit about atmospheric escape as well. So it's a little bit for everyone, I think, also solar system stuff. So let me start telling what is it that we do in my group. Okay. So here is a picture of some of the people in my group at the moment. We work with not only exoplanets, also with planets in our solar system. As Christiana was saying, I'm part of the science team of the Juno mission. So I've been working a lot with Jupiter, also a little bit with Saturn. Now I'm starting to get into Uranus and Neptune as well. But most of my group is really doing exoplanet stuff. And on exoplanets, I'm working with giant exoplanets, but also with rocky exoplanets. For the rocky exoplanets, I'm very interested in the very, very, very hot ones, the ones that are probably completely molten, more than 2000 Kelvin we are talking about. There are quite a few of those planets, and because they are the ones that are closer to the star, they are also the ones that are easier to be characterized at the moment. And I want to know more about what we can learn from those observations about the atmosphere and also the magma in the interior of the planet. On the giant planets, I'm working with interiors and also with atmospheres. So this is really what is going to be the focus of this chapter. But of course, the first thing that I want to discuss with you is what are the main questions in the field of exoplanets and in the field of planets in general, I should say. So we would like to know how is that planet work. And of course, we have a lot of information from our solar system planets. And here, I'm focusing on the giant ones. We have very detailed data from many missions, especially if we look at Jupiter. We have data from the Pioneers, the Voyagers, Cassini, even New Horizons did a flyby around Jupiter. So we have the Galileo probe that entered in the atmosphere, and recently Juno mission that has been orbiting Jupiter since 2016. But still, there are very key fundamental things about the planet that we don't know. And of course, when we are thinking in general about planetary physics, if we think not only on the very detailed data that we have in the solar system, but on the huge amount of information we are getting from exoplanets, there is really a lot that we have to learn, not only about the interior, the inner workings, but the atmospheres and how they couple with each other. So this is, I think, one of the main things that we don't know, especially if you think on exoplanets. This is a very young field. So the first exoplanets were discovered 30 years ago. So we do have a lot of information, but this is not as detailed as the information we have for solar system planets. So there is still a lot of things that we need to learn about how these planets are different. And also, this comes from the second question, that is, how do these planets form and evolve? So we have in our solar system 4 giants, very far away from the sun. And on the other hand, we are finding hundreds and thousands of giant exoplanets very, very close to their stars. And even some that are super far away, at 100 million, even more. So how is that we have all those objects? Are they forming the same way? Is there something that distinguishes them in their formation and their evolution? And how can we understand the inner workings of them? Is that all of them have the same interior structures? So those are the kind of questions that I would like to know, and some of them I will touch during this talk. Going a little bit more into the formation part. So giant planets are particularly interesting in this aspect because they are the first planets that are born in a planetary system. We have that the planets form around this disk that is the remnant of the star formation process. So we have a disk of dust and gas, and the gas dissipates very quickly in a few millions of years. So you need to form your giant planets before that gas dissipates. So giant planets are formed in a few millions of years only. Rocky planets, like our own Earth, probably took much longer. So the giants are really the ones that have in their interiors very valuable information to understand the first stages of the formation of a planetary system. So if we study, for example, if we look at our solar system, Jupiter and Saturn are very key to understand those first stages. And also, the giants are the biggest planets, so they have a huge dynamical influence as well. So if we want to understand the dynamics, the architecture, they also have a big role to play. So that's really why we want to know more about them. And this is really what motivates the work that we are doing with giant planets in my team. Now, let's go more into the motivation of working on the results that I will show you today. And here goes one cartoon that I made for a paper, for a review paper that I wrote this year. And this is Jupiter. And here is basically what we think is the internal structure of Jupiter today. So we learned quite a lot about the interior of Jupiter with the Juno mission. The way that we did that is because this mission was orbiting around the planet for many, many years. And we got a very detailed gravity map of the planet that allows us to study the density distribution in the interior. So this is really what I've been doing for the Juno mission. I've been doing interior models trying to fit the gravity data that we were getting. And this is, let's say, the most up-to-date cartoon of what we think is the interior of Jupiter, which basically has in the very center a core made of 100% metals. And then if this core is diluted outwards, so it's not that there is a distinctive core separated from the envelope. It's kind of like a more gradual and mixed thing that is happening. So we call this region the dilute core region. And this was really something that we discovered with Juno. Before Juno, we thought that the core and the envelope were two distinctive layers. But we know now that we need this transition in order to explain the gravity data that we are getting. Then we have this other layer that is dominated by metallic hydrogen and helium. And then we go to the outer part that is really the one that we can observe the atmosphere. For example, the atmosphere is actually a tiny, tiny, tiny thing here that is dominated by molecular hydrogen and helium. You have here this layer that has some droplets. This is what we call the helium rain layer. And what happens there is that there is an immiscibility between hydrogen and helium, that here they are a well-mixed solution, but at some point they just don't want to be together anymore. They separate, and that's why we have these two distinctive layers in the interior, kind of like what happens with water and oil. And this layer means that helium is trapped in these droplets, together with other noble gases, and then because it's heavy, it goes towards the center. So then we have an overabundance of helium that we expect to have in the interior of the planet. and a depletion that we actually observe in the atmosphere. And this is the case for Jupiter and for Saturn as well. You also see this dashed line here, and this is representing the extent of the zonal winds that we observe in the planet. So if you look at Jupiter, it has these bands that rotate at different velocities in different directions. Those are the zonal winds, and they don't extend all the way to the interior. They extend more or less up to 3,000 kilometers. And this is another of the big discoveries we made with the Juno mission using the gravity data, which was the extent of these zonal winds. Now, I told you that I was going to talk about exoplanets, so you might be wondering, where are the exoplanets coming? And the thing is that really we learned a lot about the interior structure of giant planets with Juno. And I'm talking about Jupiter here, but we also learn a lot about Saturn lately. And here I just put in some of the papers. They are not the only ones, but some of the papers that were really studying these problems, where we found specifically the dilute core here. It's very important. It doesn't look like a huge thing in the figure, but actually it's very important because it might mean that there is a gradient of metals in the interior of the planet. And then this picture that we used to have, that the interiors of planets were convective all over the place, might not be right anymore. We are thinking that there might be some radiative zones and some regions in the interior of the planet that are not convective as we thought before. And this is not only for Jupiter, we are only finding the same results for Saturn. Independent method that is using seismology. So the planets oscillate like the stars do, but with different mechanisms. And for Saturn, we can actually observe those oscillations because they propagate in the rings of the planet. So using that technique is how we know that Saturn has a similar structure than the one that we are seeing for the interior of Jupiter. And that is not the end of the story. We are also having better formation models for giant planets. And those formation models also are kind of finding these inhomogeneous structures naturally from the formation for more detailed models that explain the planet formation. So, of course, the question then is, what about exoplanets? So I'm going to tell you a little few things about that. First is that we didn't just have enough data to worry about these things for exoplanets before. Because, of course, we had just one data point on one specific band with huge error bars. So it was very difficult to say anything about the interiors of the planets before because we just didn't have enough good data. But that is changing. And one of the things that is driving this change is JWST. That is really giving us amazing, amazing information, specifically on the atmospheres of the planets. But I will show you how the atmospheres are actually helping us a lot to understand the interiors of the planets as well. Okay, so I will divide the talk in two parts. First, I will talk more about the interior, and then I will move more towards the atmosphere, and we are finding with JWST. And on the interiors, what we really want to know is which is the bulk mechanicity of planets. We want to know which is the amount of metals that they have in the interiors, and how are they distributed. And this is not only for exoplanets. I think we still have the same question for the solar system planets, actually, where we still don't know the amount of metals in the interior of Jupiter, or we know it with a huge error bar. So I think this is a question for all planets, which are the amount of metals in the interior and how are they distributed. And of course, this helps us to understand more about the formation process of giant planets that we are still not completely sure about. Now, what is it that we did? So this was the interior model for exoplanets that we've been using so far. Most, if not all, of the papers that you read that has something to do with interiors of exoplanets are using this model. And this model is telling us that the exoplanets have in the interior a core made of 100% metals. This core is usually quite large. And then the rest of the planet is this envelope that is fully homogeneous and convective, which means that what we observe in the atmospheres of these planets represent really the metallicity or the materials in the rest of the planet. So this is really the model that we are working on these days. And that's why, for example, we are linking observations that we make in the atmosphere with the formation of the planet. We are like, hey, if we observe a certain carbon or oxygen abundance here, it means that you have all these carbon and oxygen in the rest of the planet, and that will tell you where the planet was born. But if this model is not true, and there is something happening in the interior, then that might be wrong as well. So this is really one of the things that I want to study a little bit more. And for that, I'm trying to introduce this other model for the interior of exoplanets that, of course, we don't know if it's true. This is what I would like to know, if the planets were more like that or like this other model. This one is based on what I just told you about solar system planets, where we still have a compact core made of 100% metals, but then it's not that they are completely separated from the envelope. We have this dilute core, meaning that we have this gradient of metals when we go towards the interior of the planet. And of course, this makes things more complicated because it will mean that what we observe in the atmosphere is actually not representing the abundances in the entire planet. But it's something that we need to test. We don't know which one of these two models is the right one for exoplanets. We know that this one is the right one for solar system planets. So if it's true that all giant planets form in the same way, then probably this is the true model for exoplanets as well. But this is something that we need to test in the next years. So using these two models, we kind of worked on a retrieval. We said like, okay, we have radius of the planets, we have masses, we are having better atmospheric models and metallicities. So is it possible with this information to say something about the interior of the planet? Is it possible to say which will be the core mass that we expect, which is the metallicity that we expect? And is the same the result that we are getting if we use one model or the other? So this is really what we are trying to do. And we published a paper about that. We are about to publish another one, but this is really work in progress. It's not that I have the answer. I'm giving you the spoiler right now. I cannot tell you at the moment which one of the two models is the right one. It's work in progress. I hope to have some answers about this in a few years, but we are working toward that. So let me tell you a little bit about the model that we are using. And this is a model that is based on solar system planets. So I basically took my interior model for Jupiter and I adapted it to exoplanets. And where we do is we solve the internal structure equations. So basically model the interior of a giant planet is the same as modeling stars. The main difference is that giant planets don't have nuclear reactions in their interiors. They get their energy because they are gravitationally contracted. But essentially, the models are the same. We can even use the same models. So MESA, for example, that is a very famous model for modeling stellar evolution, is also used for giant planet evolution. So in my case, we have our own model based on Jupiter, but it could be any model that we use for stars as well. So what we do is we use some observational constraints. In the case of these planets, it's mass, radius, atmospheric metallicity, and good models for the atmosphere, for your temperature, for example. We also need the helium abundance, which for all the cases I will show, we assume is the same as the stars. And of course, that will be the same as the sun, because it's not that we have that information for a lot of these objects. So that is one of the big assumptions that we are making. And then we don't do one calculation, we run hundreds of thousands of calculations, more like an MCMC approach to find these are the real outputs that we want to get, the metals that the planet has in the interior, the metals that are in the dilute core, and the core mass. So these are really the three things that I want to know. Of course, this one is not there in the column in the models where we don't have a dilute core, and that makes those models way easier to solve for the retrieval. So let me show you some of the results that we are getting. First, we use a test planet just to make sure that the model was working. Even though I know it works for Jupiter, I just wanted to know that it works for a random exoplanet. So we created a planet that we knew, which was the core mass, everything, because we made up the planet. We created the observations of the planet, and then we tried to retrieve with those observations the initial parameters that the planet had. And the thing is that if we use only the radius and the mass, of the planet as the data to obtain our interior parameters, this is the answer that we get when we are trying to find the core mass, which is basically that it's impossible to say which is the core mass of the planet. The real core mass that the planet has is this dashed line that you can see here. So you see that we cannot really tell which is the core mass of the planet using only the mass and the radius. And that is also telling you why we had these very simple models to work with exoplanets up to this point, because this is basically the only data that we have. But if we add now metallicity information, temperatures in the atmosphere, then this is what we get. So for both models, for the homogeneous and the inhomogeneous models, we are able to retrieve the core mass if we add more information. This is not so complex, right? We have a certain amount of unknowns, and if we put more data, of course, you are going to get your answers better. So, but this is just a proof of concept to show that really having more information on the atmospheres of these planets are helping us to try to constrain the interior modes. So we are really entering, let's say, in a new era when we are going to be able to learn a little bit more about these planets as well. Now, with this model, we can also find distribution of metals in the interior. And here are, we did this for 30 exoplanets. This was actually published at the beginning of this year, so we didn't have JWST data when we were doing this. So for the metallicities, we used 30 exoplanets that had water measurements, and some of them had very large error bars, so we really used the water as a proxy for the metallicity of the planet. But we will do better in the future. But you see that for these 30 exoplanets, we can derive the distribution of metals in the interior and also the core masses. And here is the mass of metals in the envelope. And there are two colors, the homogeneous and the inhomogeneous models. And you see that the error bars are quite big in some cases. So this is a very extreme, this is the same planet, but with the two different models. And actually, these error bars are telling us that we are not retrieving this planet very well. But these ones are a little bit better. In some cases, you see that they are very close to each other, but in some cases, no. So really making some pre-assumptions on the core mass of the planets is not the way to go. So we need to learn a little bit more about that. We also try to study the mass metallicity relation. And here you are seeing the total metallicity of the planets and the total mass that the planets have. And these 2 points are Jupiter and Saturn, well, the other way around. And you see these other 30 exoplanets that we studied. So there is some kind of line here that we will find that we might have for the metallicity and the mass. We are finding results consistent with these 2 planets, but we also have things like this one here. These 2 planets, for example, have a very high metallicity compared to the mass that they have. We were studying this a little bit more, and we found that actually those 2 cases are some exceptions where the stars also have a very high metallicity. So we are wondering if maybe that has something to do with it or not. There were some studies done a few years ago trying to see if it was true that the metallicity of the planets have a relation with the metallicity of the star, and they didn't find any. So I'm not sure if this needs to be revised or if it's also just a coincidence. At this point, it's really one case, so we need to dive deeper into this. Okay, so let me just move to the second part. Before that, I would like to wrap this up and tell you that, by the way, this was work done with my student, Sane, and now I'm following up with another student. And one of the main take-home message, I think, is that we might be able to learn something about the interiors of planets with all the great data that we will get with JWST. This is not really what we used in this study, so that's also why our error bars are so big, because the error bars and the metallicity were very big before. Hopefully that will improve in the next year, so stay tuned. And now let me move to the second part of the talk that will be more talking about JWST and what can we say about the atmospheres. The whole colloquium, though, moves around the metallicity of the planets. So I will also talk about the metallicity in this case. because atmospheres and interiors, of course, are related. So really, the big question on this part is that we would like to know about the metallicity in the atmospheres, because as I just showed you, that really puts our limit to try to understand the interior. I would say is the lower limit. And one other question that we also wanted to know is how they evolve with time. And this is something that we have to worry about in exoplanets, because we are observing planets at all different times. And these planets are, most of them, very, very close to their stars. And when they are so close to their stars, they are also affected a lot by W radiation in two different ways. One is that the planets are inflated, and the other one is that they lose their atmospheres. So these are two complications that we don't have with solar system planets, and that we have to worry about in these cases. And finally, but I might skip that part, but if you are interested, we can talk later. We also wanted to know how the evolution of the atmosphere with time reflecting the spectrum that we are seeing for the planets. Okay. So how do we study these atmospheres? I'm pretty sure that most of you here know, but just to make sure that we are all on the same page, most of the atmospheres of exoplanets are, not all of them, but for many of them, we are using what we call transmission and emission spectroscopy. So you cannot see the atmosphere very well here, but this object has an atmosphere. And what happens is that when the planet is passing in front of the star, some of the stellar light passes through the atmosphere. And then what happens is that at different wavelengths, we are seeing the planet with different radii. And this is what we call a transmission spectrum. Right? So we observe the planet at different wavelengths, and we see the planet with a different radius depending on which wavelength we are looking at. And this is giving us information on the components of the composition of this atmosphere, because it's of course reflecting the opacity and the composition. So this is really how we are obtaining data for the atmospheres of these planets. And so far, we've been using instruments that were not built for doing this. We were using JWST, we were using Spitzer. But now is the first time that we actually have an instrument up there that can specifically work with exoplanets, and that is JWST. So this is really creating a true revolution in exoplanets these days. And that is because so far we have information of around 30 planets, that are the ones that I showed in the previous part. Now, with only the first 2 cycles, we doubled that number. So not all the papers are out yet. People is working with this. We are trying to understand the instruments and data, but you will hear a lot about exoplanet atmospheres in the next years. Sorry. So in particular, I want to talk about one guy. It's WST-39b. So the reason why I want to talk about WST-39b is because probably these days it's the planet that we know the best. It's a Saturn-mass planet. It has an equilibrium temperature of around 1,000 Kelvin. So it's a typical hot Jupiter. It orbits the star, it's a G star, and the period is 4 days. So it's very, very close to the star. Not as close because the temperature is 1,000, that is, you know, not so cold, not so hot. For an exoplanet, it's okay. But it's really the pet planets that we took to try to understand how JWST instruments were working. So this was the one that the early science team did, and this was observed with all the instruments in JWST. And this was done by a team of 300 people. Some of the people here is part of that team as well. And there are some great results that are coming out of that. Here, what you are seeing is this transmission spectrum that I mentioned before, and this is for one of the instruments. This was the very first paper that was published by the early science team last year. And you see here these 2 points with these huge error bars is the data that we had before. This is Spitzer data for this planet. And here overimposed, you see the JWST data that we are finding these days. So it really shows the improvement in the field with these instruments. What you are seeing here, this bump, is CO2. So this really confirmed was the first detection of CO2 in an exoplanet atmosphere. This was the first paper, but it was followed by many others. And actually, if you are interested, all of them were published in 7 papers in a special edition of Nature at the beginning of this year. And here I'm showing some of the other examples of other detections that we've made. So here again, you see the CO2, but then with another instrument, we also detected water. And here, particularly exciting, this tiny, tiny bump that you can see here. So this is again the CO2 feature that I mentioned before. And this next to the CO2 is SO2. And it was the first detection of a sulfur species in an exoplanet atmosphere, which was also very exciting. Talking a little bit more about that sulfur detection, you can also see it here. So this was specifically studied in a paper by Shamit Said as a first author. And what you can see here are the different models. So the lines are models showing how different metallicities in the atmosphere actually are affected by this SO2. So CO2 as well changes with metallicity, but SO2 is actually a great molecule to test the entire amount of metals that an atmosphere will have. And that's also why it's exciting, this discovery, not only because we are now detecting sulfur species in exoplanet atmospheres, but also because, particularly interesting to me, sulfur is a good indicator of metallicity in the atmospheres. So if we can detect sulfur and SO2 and CO2 in many more planets, that would be great to understand more about the metals in these planets. Now, how is that the planet obtained that metallicity? So far, we think that it's enriched in metals approximately 7 times compared to the star. We also see that planets are enriched approximately 10 times, same when we go to Uranus and Neptune. So the question is, why are the planets enriched? If they are born from the same gaseous disk that gave birth to the star, at the very first level, you would expect them to have a similar composition. So there are different things that can happen. One might come from the planet formation itself. So, of course, planets are not born from the entire gas that is in all the disk, but they are born in a certain place. And we know that there is chemistry happening in protoplanetary. So that might affect not only gas, but they also create solids. And then if they are solids that might enrich your gas. So this might also be a reason, right, why we are not finding the same metallicity. So planet formation has probably a big role to play. But the other way that planets can acquire their correct metallicity is through the evolution. Because we know that they have this escape happening, that the lighter elements are escaping, and then that might create a concentration of the higher metals in the atmospheres. So maybe we are also seeing that evolved planets have higher metallicities than very young planets. So these are some of the ways that a planet can get their metallicity. What we decided to study, what I will show you, is this second part. And it's really to know if WST-39b got its metallicity, current metallicity, because of the evolution of the planet. And there are lots of uncertainties here. One of them is the age of the planet and the star. And this is really something that we hopefully will improve with one of the missions that actually many people here participate, that is Plato. If we get better ages for the stars and the planets, that will really help to understand more about the evolution and about the scale. And even the scale mechanisms themselves. So we are not, we don't know very, very well how what happens with the metals. So the light elements escape, but if the escape is very strong, it drags some metals as well with it. So there are still many questions here. So we did a first approximation. And this is more or less the methodology that we are using. So we evolved the planet and the star, and for this we use the MESA code actually. For the evolution of the planet, we put together the MESA code with a hydrodynamic escape that was done actually by Daria. And this includes, in the calculation that we did, we also include the drag of these metals when the hydrogen is escaping. And this is with a very simple approximation made by Juno and Cassini. We then stopped the planet at certain times to try to study more their atmospheres, because we wanted to also understand the evolution of the spectral features with time. And then for this, we did first chemical equilibrium calculations, and then chemical kinetic calculations, with radiative transfer. So we did all of these cell consistently at certain ages. And finally, we modeled the effect. So I think I will focus more on the first part. But if you are interested, we can talk about that. So the first thing that we have to consider is that, of course, the planet that we are seeing today probably was not the planet 9 billion years ago, right? So it probably has way more mass. So then we made a grid of models with different initial envelope fractions, because we also don't know how big was that atmosphere, and different initial masses. We evolved all these planets, and the ones that you are seeing here are the ones that at the end got the radius and the mass that we are observing today. So actually this grid was way bigger, but we are only keeping here the ones that at the end were similar mass and radius as was 39. And from here, you see this square is actually what is zoomed in here. So this is the most extreme case that we found for the state of metal. And what you are seeing here is how this metallicity increased with time during the evolution of the planet. So you also see these different times, that is when we were studying the atmosphere with more detail. And essentially what you are seeing is that the metallicity doesn't grow that much with time. And this is because this is a Saturn mass planet. Of course, the escape is more extreme when we have smaller planets like Neptune size, for example. The escape is very extreme with those. But when you go to giant and giant planets, is nothing compared to the 300 that they might have. And we are also seeing that with the atmospheric enhancement, because the light elements are escaping, they drag also others with them. And that's why we don't expect a huge enhancement in metallicity, at least with a very simple model. So then I think that the main conclusion that we can say is that, well, WASP-39b probably obtained its current metallicity mostly in the formation process of the planet itself. Now, I put this with a question mark for two reasons. One is because we are making a very simple model here. And the reason why we use a very simple model is because we wanted to evolve the planet at the start, and applying that to a hydro code was time consuming, so we made some simplifications. So it would be interesting to know if this holds with a more detailed model. The other reason, the other big caveat, is this that I told you before. So this would work in a model like this, that is telling us that the mass is escaping here, and what remains of the planet has the same metallicity. But if the planets are more like this, when the mass is escaping, what happens is that you are seeing more the enriched parts of the planet. So maybe this metallicity that we are seeing is actually this gradient of metals that the planet have that are seen when the planet lost its lighter elements. So we still don't know about that. We need to work also with this coupling of better interior models and atmospheric escape to try to understand this better. And it will be very interesting also to smaller planets, because we have this huge desert of planets that we think lost a lot of their atmospheres. And we don't know if what we are seeing are exposed cores of those planets. So this is definitely something interesting to study in the future. I will finish here because I hope you have many questions. First, let me remind you of the first part of the talk that was mostly about interior work, mostly made by Hanne. Second part was more about the atmospheres, and here I showed work not only by me, but really the entire ERS team was working very hard. It's a team of 300 people, so it was also very complex to organize, and it works very nicely. I think it's a very good example of how the collaborations should work, at least from my side. We are also studying the evolution of the metallicities, probably, at least thinking on very simple interior models, WASP-39b could have acquired its metallicity mostly from planet formation. And I also have to thank all my collaborators here, and thank you for your attention.
Okay, so I think the floor is open for questions. I was told that the new sound system should pick up actually your question without this microphone. but let's see. I mean, maybe the online people could give us feedback later. So, yes, please. No, just speak up. Yeah.
This is what I want to. I wonder to which extent the models with the diluted core are compatible with the planetary magnetic dynamo model. I'm afraid the latter are in troubles if there is no core and no convection zone.
So the magnetic field of Jupiter is not really generated in the core. It's generated in this
core, but due to dynamo, which assumes the presence of the core and the convection.
Sure. But so I don't have images here, but I can refer you to the paper. So we have a very detailed map of the magnetic field. It has different components. The main dynamo component we think is generated in the metallic hydrogen part. So it's very higher than the core region. So that is mostly where the dynamo that we observe is coming from. If there is an inner, also dynamo generated in the inner parts, we probably are not seeing that because of these stable regions. And it's also backed up with the data collecting. So we do have issues from the dynamo for that. Also for the heating brain part, we also think that might be the unstable region. So there are some new models of the dynamo.
Yes, this is what I mean. So the dynamo has to be revised in that sense.
It's very high. So this doesn't affect that.
There are essentially different features which have to be verified because, yeah, I don't know, but the work.
Yes, so we are working. So Jeremy Blockman is the one that is mostly doing the dynamo.
The surface dynamo is quite different. I wonder how you can explain the huge magnetic field of the giant Jupiter.
It's the outer parts. So the metallic hydrogen part has enough metals, and the hydrogen itself to generate.
Okay, maybe some other questions. Students, maybe? Students first. Are you a student, Gabriel?
No.
You mentioned that Jupiter has a thin molecular layer, which is the atmosphere that we tend to observe. If I missed it, but is it the same for Saturn from the Cassini data?
Yeah, so what we observe is just the tiny part. So with Jupiter, we have more data because we have the Galileo probe that enter up to 20 bars. So we know up to 20 bars, at least for that part. For Saturn, we didn't have a probe. So the only information that we have is remote. And then when the atmosphere is optically thick, you don't see it anymore. So we have a microwave radiometer on board of Juno. And the idea was to see below the clouds. It's been very tricky to understand the data that is coming from that. So we only were able to say something about the water abundance in the equatorial region and the bigger bars. And this is the best that we could do for below the clouds. But it's the same with Saturn. They are very similar, actually.
I assumed it would be, but
Gabriel, I think.
Okay. Do you mind going back on your first part of your talk when you show your test planet for your model? Because I was not, I just have point out something because you say you can retrieve the planet, but the core mass fraction is at 0 and it peaks at 0. It seems that if you would have chosen a test planet with a different core mass fraction, it would be clearer.
Yeah,
it's not like a noise as a.
Yes. So we did a few other tests. It's true that this line is at 0, but it was a little more.
The problem is not that it's at 0, but it's at the first bin, which is where the peaks, and it looks like your retrieval has some sort of tendency to have some noise going down, right? And if the core mass fraction was somewhere else, and you would have a peak there, it would be clearer to say that we can actually retrieve it.
So we tried a case up to 0.2, and it was working okay. We didn't try more than that.
Okay.
Maybe I should put that next, because you're right, that it would be better to see it in the middle.
And my second question is, in terms of instrumentation, what is the most important thing you would like to see? Is it remote with, I don't know, spectroscopy, or is it in situ, as you said, the Galileo probe, maybe some entry probe on Uranus or something?
I have different answers for that, depending on which object. So for solar system, I would love to see more about the oscillations. So we are studying oscillations in Saturn for the rings. I think it would be awesome if we could measure oscillations in Jupiter as well, because really that seismology is really what can go all the way to the core. And with these models, we have limitations because the gravity data, the higher the harmonic that you observe, the higher the outer you go from the core. So if we have some limitations on the information, that's why for Jupiter we put a maximum core of 7 Earth masses. I don't think we can say any better than that. The neutral region though is very well sampled, but the core itself is very hard. So for solar system, I would love to have seismology. For exoplanets, I did a continuation of this that I didn't show here, but if you have log numbers, that can give you an extra information, and that really impacts what we can retrieve of the core. So log numbers would be amazing. I know that Chaos is trying to find some log numbers of exoplanets. I've seen also some theoretical papers about that recently. I'm no expert, but I think that those measurements could really help.
I mean, it was already sort of asked, but I would like to know. So it's clear that if you use all these five observables, you get a much better constraint. How do you say that? How do they rank? Like, what is the best single observable? Or say the best two?
Yeah, we tried one by one. Helium really makes a difference because helium is the second most. So we have hydrogen, helium, and then the metals. Yeah. So helium really makes a difference. No one really mentions that in interior paper models, but we are all using the solar elements, so that might make a difference. I think.
But there's no way to get helium from data.
No, but if we can get it for stars, then we can at least assume that the stellar helium abundance is the same level of the planet. So that would be great. And then the metallic. So helium goes first, and then the atmosphere.
Yeah, so I have a comment. Maybe you show these figures where you compare the two different scenarios in the evolutionary escape issue. The next, I think. Yeah, the illustration. What is it? The blue, yeah.
Okay, yes.
So because you mentioned it could be when you take if the from my side the right one is the more accurate case or more realistic, then it may be a problem. You do not know if the evolution was different that you or the initial content was a different one. But I think what you could do is if you, I don't know the star, of course, but if it's a, I don't know, G star or whatever, GMF, there is some knowledge about the range of the UV evolution, as you know also. So you could initially set some different ratios you may expect and then model them over the different evolutionary paths. And if nothing changes, you can be sure that it is very close to the origin.
You mean observing planets?
Yeah, if you take the planet, and yeah. I don't know, let's assume, I mean, you know the star. I don't know. If it's a G star, we know that there may be a range of evolutionary paths in the history. First begin here, yeah, yes. Where the escape is most efficiently. And I have to say, I don't know the paper and so on. So maybe you used an average evolutionary path or a range of evolutionary paths for UV fluxes. Yeah, for the UV fluxes. But what I mean is, if you start with different assumed metallicity ranges and nothing changes over the different evolutionary paths, that means if you have a high escape and you do not reach the value you expect, or if you use a different initial content, then you can be very sure that this what you see is not much different than the initial one.
I'm not sure I follow, but maybe we can chat later.
Yeah. Okay. Yeah. The second is from the secret slide from the left. I found a question. I will forget it when I move out of the. You say so. What we saw is that there's some evidence of CO2, as I remember, and there was the other slide where there is the pressure levels. Is there some? I don't know if it's some pressure values of. You know, you can have from a Mars to Venus, whatever pressures. A bar, 100 bar. Something like this, or is this not? I mean, it's a rocky planet, so there should be the rocky planet, and you have a CO2 where you. So it's not the info is not there somehow. Some pressure levels you may need. I don't know. I have no idea if you can observe a millibar CO2 or it has to be 100 bar or whatever. Yeah.
Okay, so the observations are around 0.1 knots.
So very, very low.
Yeah.
Good. That's exactly what I predicted, more or less, on such a planet.
Yes.
Yeah, but this is, I think, some magma stuff
Yeah,
which goes continuously.
Okay, it's done.
I have two questions. I have two questions. So we have talked about SO2 and say this gives an idea about the mechanism. Why do you think SO2 gives an idea about the mechanism? Of course, I have my second point behind it, which probably discuss it all.
It's really a trial and error. So we did models. There was a paper that we did last year with actually Miguel in the Coleman and Ren's plotters, studying different to sulfur to oxygen ratios and carbon to oxygen ratios and see how that affected the metabolism of the plant. And somehow the feature of CO2 is so strong that even if you have a lower density, you see the feature, but the feature of SO2 is really dependent. So you need to have a very high density to see the feature. So it's more dependent on how we see. If there is no physics, well, probably there is. But in our case, it's more a real study that we did on the remember we did this paper and we did predict the workshops in 55 countries. Well, if I see a temperature pressure profiles, and the trends are higher, so they still last. So we really want to revisit the real story again. Absolutely. So the only is on that. Really? Yeah. So we can talk about that.
Okay, maybe I think another question, please.
Because you said that you can't get helium. That's not entirely true. There's the helium-1 triplet line, one micron at high resolution.
The atmospheric escape. The escape.
That's the problem, right? The problem is like it's the exosphere, so probably it's probably a very weak proxy for helium, right?
Yeah, it's not really giving us that one.
Too bad. But can we, I mean, on the other hand, can we maybe go back with atmospheric escape equilibrium models and then feed that back to helium? I mean, go from
I have more hopes on the stars than the planets.
Okay.
On that side. There are some papers that I skimmed through about helium protoabundance in stars, but they depend on models as well. So I don't know much about that, but I'm trying to learn more. Because
but it's the same problem. I mean, how do you want to get helium from the star, right? I mean, it's the same.
Yeah, so for example, Jupiter and Saturn, we assume that they have the same abundance of helium as the sun.
Yeah.
Because helium is a noble gas, it doesn't.
Yeah, exactly.
So also if you get the one at the star, you can assume that the sun will have the same.
No, but here the escape is very efficient, probably. I mean, maybe not as this Saturn, but because we have some studies for small planets now, depending on the V-evolution, everything, mass and so on, and on the primordial atmosphere, it's possible that you enrich huge amount of helium over some time. But on this, so there's really these big planets, and then when you go to the Neptunes and sub-Neptunes, then this becomes
Yeah. Now I don't even start with the previous so far. Smaller does not have more complex.
Now, mostly using my authority as organizer. Last question. You mentioned this very interesting at the boundary where helium gets too hot, so we have this condensation phenomenon of this ring out. I wonder, is helium special there, or can we maybe have also other substances doing something similar further inside? When you have this kind of more gradual change, maybe other phenomena like that?
We are studying that for the smaller plants, like for ice giants. If you have enough amount of water, for example, you might have some instability of water and methane. There are some studies being done on that. For these ones, though, because they are mostly hydrogen and helium, any other thing won't matter that much.
But I mean, as you go inside, as you said, the concentration levels decreases. And
yeah,
so at some point, maybe other
substances. It might happen. To be honest, no one studied that before. Not even these hydrogen and helium invisibility in giant exoplanets have been tried before. I think I've seen only one paper about Jonathan for me, like 2000, and that's it. So we don't know.
Okay, so thank you very much, and thank you to the speaker. Please go ahead. If somebody's interested to join us for a restaurant, let me know. It's 6:30. I will tell you, where it is. I don't have it in my mind. But if anybody wants to join, just let me know. I do.
That's still sorry.
Yeah, it's in half an hour though, so that we give Yamila time to chill and other people time to question.
And then it was very dry. So forever.
There was one paper when they say it could be that
well, you can explain the 100 bars from the grades. But from the data, from these data itself, we are seeing just the upper atmosphere.
You can also move actually.
But if you want to have coffee, you have to bring it all back.
Yes, you have to bring your cup.
No, they say we want them.
But they maybe my later. I watched it and then it makes it.
No, I get you. Probably.
They have basically all.
Okay. So these very formal. How do they pull? Are they stable? Do they stay the same for years, or is there a trick you can do where you take eventually you should do that?
No, that's a great question. So we think that it was more like the evolution almost. The other idea was that maybe where they was before.
Yeah.
The convention, so you actually have whatever. And if the gradient is very steep, and then you don't have convections.
Right. I guess if you don't have the convection, you can't evolve it at all, and it doesn't settle the gradient. Velocity doesn't.
It changes a little bit, but not that much. And so I don't have that.
On one level, I'm disappointed, but I'm excited for you because you can actually just put them together in one H pin